All right, so we're working on, these are the answers for WorkEnergy Assessment 1A. All right, number 1 says, what does the energy pie charts tell you about the behavior of the object?
You just have it's moving to the right at a constant speed and then comes to a stop.
So I love this. We don't know whether it's moving right or left or up or down. We just know it's moving. Because kinetic energy itself doesn't have a direction. So it's moving. What do you know about its speed?
Constant speed.
That's right. How do you know the speed's constant?
Didn't it say?
Well, what do you notice about the kinetic energy in the first 4?
It's all the same.
That's right. If the kinetic energy is all the same, what does that tell you about the object? It's moving at a constant speed, right? Yep. And then, in the last one, it's empty, true?
Yeah.
So if in the last one, if there's no kinetic energy, what does that tell you? That it had to come to a stop. That's right. So A, or number 1, really says, what do you notice about the behavior of the object? It's moving at a constant speed, and then it stopped. Number 2 says, suggest a scenario, and then fill in the unlabeled portions. So what did you guys suggest?
So it was elastic because it's moving and it's a spring.
This is a great suggestion, right? Think about a block that's moving at a constant speed that encounters a spring, and the spring brings it to a stop. Is that reasonable here? Absolutely. Or it could be like a car moving, or a block moving along a frictionless surface and then hits a rough patch and slides to a stop. So that would be thermal energy instead, right? Or it could be a block that was rolling along a flat surface and then went uphill, right? And as it went uphill and came to a stop, maybe it's gravitational energy. Would all those be reasonable? Yeah, totally. Okay. I think it's great. Thank you so much. 3. Oh God, this does not bode well. Go ahead. What's it say?
Soon after jumping out of a plane, a skydiver falls at a constant rate, usually around 120 miles per hour. His gravitational energy is decreasing. Why isn't his kinetic energy increasing? We said it. He's flying at a constant rate, so he isn't losing any kinetic energy.
But that's what it says in the problem, is he's going at a constant speed.
He's going at a constant speed, so he won't lose or gain any kinetic energy because it won't go anywhere.
But why not? He's falling. The gravitational energy is decreasing. The gravitational energy is decreasing. Where's the energy going?
Go down?
Going. No, the total energy has to stay the same.
Yeah, it's going to.
So normally when you drop something, let's say you drop something in the classroom. Okay? If I drop something in the classroom, this falls, the gravitational energy goes down and the kinetic goes up. But this is a different situation. The gravitational energy is going down, but the kinetic energy is staying the same. How is it possible that even though the gravitational energy is decreasing, the kinetic energy is staying the same? That's the question.
Thermal energy.
Tell me about that.
It's going into thermal energy.
How?
Friction between the skydiver and the air.
Ooh, what do you guys think about this? Does that make much more sense now? Okay, so as the skydiver's falling, he's rubbing hard on the air, yes? And because he's rubbing on the air, all this thermal energy is being generated. So instead of the decrease in gravitational energy going into kinetic energy, it gets converted to thermal. That makes much more sense. We know that thermal energy can be generated if you're rubbing on the air. If you've ever seen or talked about, and we can talk about it right now, if you're in a spacecraft coming back from outer space, you enter the atmosphere going at like 17,000 miles per hour. And that spaceship rubs on the air really hard. And it heats up. And they have to have special heat shielding on the spacecraft so that it can, basically it heats up but then dissipates that heat really easily to the air that it's rubbing on. If it doesn't, the spaceship will heat up and then explode, which is not good for people. It's very bad. Good, I like that. Thank you. What's that?
Like that guy that jumped out like a Red Bull sponsored guy, or did he just have a suit that did the same thing?
So he was rubbing against the atmosphere, but he actually ended up going fast, but he jumped from rest. So he never was moving fast enough to create a huge problem. For it to create a huge problem, because it wasn't really going that fast. All right, what's the problem say? Can you read it real quick for us?
Problem says, in a class, the student held a bowling ball and against his shin and let it go, hoping and praying that it wouldn't smash him in his teeth upon its return. Explain why this is a purpose safe demonstration. Answer is safe because some gravitational energy gets transferred to thermal, so the ball coming back is less kinetic.
So this is okay. This is not. I mean, we can do a little better here. So as this ball swings, okay, as this ball swings, is there some rubbing?
Yeah.
Where's there some rubbing?
Air.
All right. Does the ball rub against the air?
Yeah.
Absolutely. Is some thermal energy generated? Where else is the ball rubbing? At the pivot point. True. Right? Is some thermal energy generated there? Totally. Right. So what that means is that energy has left the system, right? So when you release it from here, it's all gravitational energy. Then when it gets back, it's again all gravitational energy, but minus the energy that was released to thermal. Does that make sense? So if you have less gravitational energy, what's that going to say about the height? It's going to be less height. Okay? So that's really what we're talking about, is we're comparing the instant that you release it here to when it gets back to here. And if you've lost some energy to thermal, you're not going to have as much gravitational energy, so it can't go as high. Is that cool? All right. Oh, God. What's happening here? All right, this is numbers 5 and 6. So some people are upset about 5. I understand why. Can you read 5 for me?
Consider the section of the roller coaster depicted in the diagram. 100 kilogram cart starts at rest, moves along the track, and comes to a stop as it compresses a huge spring at point B. Rank the total amount of energy from least to greatest and justify your answer. So we said that A, B, C, and D were all equal because it doesn't lose any energy to friction. So the amount of energy in the whole system stays the same throughout the whole track.
Yeah, so we call that the law of conservation of energy. The total amount of energy stays the same, right? Some people thought it was a cheap question, and they're a little upset because it says rank them, but you really can't rank because they're all equal. I say settle down, okay? Like if you I mean, this is the question that is designed to say, do you really understand the law of conservation of energy or not? So yeah, so A, B, C, and D are all the same because the total amount of energy stays constant. That's why all your pie charts are the same size. Cool? All right, what about 6?
So then for 6, it says create a pie chart for each of the indicated points, A, B, C, and D. Be sure to include a key, assume a frictionless scenario. Label each arrow with the force diagram.
So there used to be arrows between them. That's the way we used to do this, but I've gotten rid of the arrows, so don't worry about the arrows.
Okay.
All right, so tell us about the pies.
So for pie chart A, it's all gravitational, it's not moving, and it's 30 meters above, so it would only have gravitational energy. And then B would have 1/3 gravitational and 2/3 kinetic because it's 10 meters above and 20 meters less than the start point. And then C would be all kinetic because it's at 0 and it's moving. And then the last one would be 2/3 gravitational and 1/3 elastic because it's hitting the spring and it's 20 meters above, so it'd be 2/3 gravitational.
Is that cool? All right, it's good to me. All right, and the last one?
For number 7, you need to create bar charts that compare the energy at A to the energy at D, and you need to assume that there is some friction present. So for the system between the bars, we have the cart, the spring, and the G field. And obviously for the first chart, it's all gravitational force because it starts right at the top of the track. And then it loses 1 block of thermal energy to friction. And by the time it gets to D, there's 2 blocks of gravitational energy because of its position, and 1 block of elastic energy because of the spring.
that cool? Does this match what you guys thought? All right, I like it. Well, so that's enough for this. I think that we should probably have the reassessment of this sometime in the very near future. But what I want you to do now is erase your whiteboards, return to your seats, and let's see if we can't do that WorkEnergy Assessment 2B.